Hello, everyone.
Good morning.
Good morning.
Good morning. Ready for another exciting action-packed day?
Well, it's Monday, so I don't know how action-packed it will be.
I completely agree with I'm just like, I don't know what he's talking about, but hey, we'll give it a try.
It's a day that you get to have astronomy. I just can't think of a better day.
Did you get my message to you in Canvas inbox?
Yes,
Okay,
I did.
I just wanted to double check.
Yeah, I did. Thank you very much. At least I remember seeing it. Let me double check, make sure I know exactly what you're talking about before I completely commit to that.
When's that test being released?
It just was not 2 minutes ago.
Oh, well, I guess I should have looked at Canvas.
You know me, I don't like to wait till the last minute. That'd be horrible.
When's it due? Sunday?
Yeah, it's due Sunday at midnight.
Cool.
When is the second part of last week's lab due?
It says it's due on the 24th.
Yeah, thank you.
Okay.
Yeah, the 24th. That should give you plenty of time, I think.
How many of the labs are required, by the way, for like?
I don't remember putting a limit on it. I used to back when we had physical meetings. I think it's more a matter now of the number of zeros killing your grade is the more pressing issue. So it's not a,
Right.
a set thing.
If
But
we
yeah,
miss
it could harm you
one-
via that.
Yeah, if we miss one, like,
No biggie.
okay.
In fact, I usually drop at least one lab grade. So if you miss one, it's not going to be a problem at all.
Okay.
Okay, good, because one that I can get really not want to do, just be like, screw you, I'm not doing it.
Yeah.
Well, sometimes we have this process we have to go through that makes one lab super important. So be careful with that in other classes, as well as certain assignments, because some of them we have to use to assess our program, our teachers, our courses, stuff like that. So sometimes you'll get an instructor really chomping on you to make sure you get an assignment done. And that's
Right.
because that particular assignment's been chosen to do some stuff. So just be careful of selectively choosing not to do ones.
Is it the moon project one?
Oh, no, there's nothing going on for this class right now, so there's none of them like that. I would say the moon project, because it's worth so many points, is one you definitely don't want to miss. Plus, you have so many chances to get so many more points beyond what the grade is. So I would say don't drop that one, but it's not because of that. And in the face-to-face class, I usually make that pretty harsh. Like if you don't turn that in, it's like 700 points off or something like that.
Right. Where do we check, like, other than like tallying it up ourselves? Like, how can we know how many points we have roughly?
It's supposed to be in the Astro points. I think you guys see it as a row in your grade book. It'll say a percentage, which is stupid. It automatically does a percentage. But if you look at that, I think you can click on it. It'll tell you the total number of points you have. But that's only the ones that I've submitted a grade for. So it's like every day, students turn in certain ones, and I wait till I get one assignment nearly full before I actually grade it. But yeah, if you the other way is you just go through your grade book and look at each one, and then you'll have a rough idea. Because you'll see like a little time clock or something like that on our book. I can't remember what it is, where I haven't actually graded it. So you can just one by one take the number of points each of those assignments are worth and add those up. That gives you a good estimate, and it's fairly accurate. Like very seldom do I give you a less, and but I do occasionally give you more points. So that's a good way of keeping up. But usually by the week before exam, you'll have a really good idea. A week or two before the final exam, you'll have a good idea exactly how many points you have, because I usually make sure I tally it all up by then.
Okay. For like an A, what's like? There's like a certain, so like I know that if we do like all the main assignments, like labs, like the smart work, all the tests, like we do okay on, that's not like a guaranteed A, right?
No, it's really a
you have
great,
to do the extra like stuff like the reflections and some other stuff.
Now they help you. So once you have to get a minimum of 1,500 if I remember correctly, but then 2,000 is where you get 3 points added to your test average. So your test average, well, your grade computed with your test average and your homeworks is your course grade. So that's a constant average. You can easily check. It also, I think it even shows it in the grade book as course grade or something like that. So you can constantly keep an eye on that. Now, if you're 3 points below that, then you need to make sure you have 2,000 astro points, and you should get enough. If you're 5 points, and you want to make sure you get 2,500 points, and if you're 7 points below that, you want to make sure you get 3,000 points. So that's how you get back into that A category or B category or whatever you
Right.
want.
Because like I'm at an A for all the tests and like the smart works. And then on the midterm I got like an 85 or something. But
Right.
would that like
That shouldn't be too bad because if I remember correctly, didn't I make it 20 and to make it 20 and 20% for the two for the midterm and the final? So 85% of 40, you know, that's still 35 points or whatever. So you're only down by 5 points. So you should still be in it. I mean,
Yeah,
I checked syllabus.
so probably a few like reflections or something would like top it off.
Yeah, reflections, making sure you get to that next critical point. Like I see so many times students will have, you know, 1,300, or no, they'll have like a 1,952 points. I'm like, you know, if you kept track of your points, you would have known better than go under 2,000, because that's where you start getting points. Same thing with 2,500. You'll see people that are literally like 75 points shy of having 2,500, or, you know, 15 points shy of having 3,000. Just make sure you get to that next one, and that'll help you.
Cool, thanks.
Okay. Yeah, you might even take your grade book. If you look at that section, actually not your grade book, but look in Canvas, there's that section that says turn in after points here. Just like cut and paste that, put it in a document, and then like put right next to it how many of those you've done, and that'll be an easy way of tabulating your astro points, so you can always keep track of it yourself, and you can keep me from making an error. I shouldn't make errors anymore because I've got it set up where there's a column for everything in the grade book. So since you have somewhere to turn each one of them in, I never lose them because they're stuck in Canvas. Okay. Any other questions? All right. Well, we're starting chapter 16 today, and this is where stuff really starts getting interesting. We're starting to learn about stars, their lives, how they end, how, you know, what makes the difference between why one dies one way, why does some become black holes, why does some become neutron stars, why does some become white dwarfs, stuff like that. So that's really what we're starting to talk about now. And chapter 16 is on low mass stars. So we're going to get started with that now if I don't have any more questions. So I'll start by sharing my screen. I should let you know that I'm basically using the material from obviously Kay, Palin, and Blumenthal's textbook again. This is the Evolution of Low Mass Stars, chapter 16, from their 6th edition of their textbook. I am going to make this full screen, and then I'm going to make it view like this. And it's always best really to state these learning objectives. I don't always do it on my online classes because I expect you guys to be sort of walking along with me in the book. But in this instance, I'm going to make sure I do it. It starts off in this chapter with a really wonderful picture of a planetary nebula, basically a star exploding that in the ancient past would have looked like a planetary nebula, which they said basically anytime something looked like a planet but was a little fuzzy, they called it a planetary nebula. Turned out to have nothing to do with planets. But anyways, that's what the page 4039 photo is. By the end of this chapter, you should be able to estimate the main sequence lifetime of a star from its mass. That's a simple calculation you can do for your homeworks. I'm not going to make you do it on a test, but it's basically if you multiply the lifetime of our sun, which is 10 billion years, if you multiply that or divide that by m to the 2.5 power, then you'll end up getting, and that's m in solar masses, by the way, then you'll end up getting the lifetime of that star. So it's 10 billion divided by the mass to the 2.5 power, or you could do it times and make it a negative 2.5 power. Again, that's something you'll do in the homework, but not in the actual tests. Learning goal 2 would be explain why low mass stars grow larger and more luminous as they run out of fuel. Learning goal 3 is to sketch post main sequence evolutionary tracks on a Hertzsprung-Russell diagram and list the stages of evolution for low mass stars. You'll see there's a horizontal branch and then an AGB branch and another horizontal branch and all sorts of crazy stuff. Describe how planetary nebula and white dwarfs form, and then 5, explain how some close binary systems evolve differently from single stars. So those are all, pretty good goals. And as always, you can try to make use of those. By the way, everybody, I did make some reflection questions for, I believe, chapter 14 and maybe even 15 last time. So you now have access to those if you want. Some of them are just making you go through simple multiplication and division problems to do a quick calculation to determine the lifespan of the sun versus the lifespan of the sun if it could burn up every bit of its mass. So that's kind of a neat little calculation. And it's just fun to see that you can actually do that with just basic arithmetic. You're literally multiplying and dividing. There's nothing more complicated. So I hope you give that a try. And like I said, there's several sets. So you got plenty of reflection questions. I've started putting due dates on things. I had a student suggest that some of my students may be missing online tests and other deadlines because my Canvas course doesn't warn you, hey, you've got this due in such and such days. That's because I learned some time ago not to use due dates. Due dates actually are what tell Canvas to post a warning to students. Well, due dates are also the thing that when I find out a student missed something and I open it back up so they can take it because they had an excuse, that due date not being changed will not let them do it again, even though I opened it back up for them. So that's why I stopped using it, but I've decided to start using it again. So hopefully you guys will get a little more help. So here it is. This is a cool picture of that planetary nebula. You can see it sort of looks like the one that Cosmos uses on their logo. The series, Cosmos series, season 1 and season 2 by Neil deGrasse Tyson. And this is called the Ring Nebula. And they're wanting to know, is this the future of our sun? And well, it might be. The problem is we have these really good models and they explain a lot of different things that can happen, but literally it's a chaotic event where, very small changes to very small aspects might cause huge changes thereafter. That's the definition of chaos. And because of that, it's not so easy to tell exactly what the end game for our star is. We have a broad brush picture, but it could depend on, well, our sun actually had this blob of matter that was, iron, a larger fraction of iron than all the other ones. So it acted a little differently than one that had less iron. Little weird stuff like that. Could be something like there was happened to be something in the way of one way of exploding, little weird stuff. So how is the lifetime of a star dependent on its mass? Again, it's basically the way you go about calculating this is you realize the lifetime of the star depends on, one, how much mass it has. The larger the mass, you expect the larger the fuel tank, right? So the larger the mass, the more fuel it has, and then you divide that by the luminosity. And it turns out the luminosity depends on the mass as well. And that's where that m to the negative 2.5 comes from. How do stars change after leaving the HR diagram? We're going to show you that. I kind of get aggravated with the way your book does it. The several first diagrams slowly walk you through what it's doing at each point, but they don't show you until the very end the entire path. I wish they showed the whole path from the beginning. So you might want to flip back and forth to that last photo just before section 16.5 as we're talking, so you can get an idea of where you're going when we're going over that. What is left when low mass stars die? So, you've probably heard it's white dwarfs, and that's essentially it. But there's actually different types of white dwarfs, and what they're made of is different and all sorts of cool stuff. And then finally, how do stars in a binary system evolve differently than single stars? You can see this is sort of a rendition of the learning goals. Sometimes misses a little bit, but this one's actually almost dead on. So here's a Hertzsprung-Russell diagram. Remember this main sequence is basically the solution set. These are the various mass, luminosity, temperature relationships that obey those equations of hydrostatic equilibrium. Once those hydrostatic equilibrium equations go off kilter, then things leave the main sequence, just like before they reach the actual star state and then their protostar state, for instance. They're not necessarily on that line either, so they tend to be somewhere else if you just plot luminosity versus temperature, or luminosity versus Wien's law's wavelength or whatever. They're going to be at different places, and then once they get just that equilibrium position, boom, they land somewhere based on their mass on the main sequence. Up here, remember, we have the supergiants, the giants, the subgiants, the white dwarfs down here. Those are all going to come into play. So recall from chapter 15 that young stars change their position on the HR diagram. They do not stay on their main sequence their entire lives. Stars only stay on the main sequence as long as they fuse hydrogen and the helium in the cores. Remember, that was the definition of when a star becomes goes from a protostar to a star. That's also the definition of when a star stops becoming a star, when it stops efficiently fusing hydrogen and the helium in the core. Stars only stay there as long as they're doing that. Eventually, they run out of hydrogen in the core, and it turns out, at least with the low mass stars that we're dealing with in this chapter, there's several tranches of star sizes that we classify, and we're using one here where there's not a lot of circulation go from the core to the outer parts. When you get to those lower mass stars, it turns out we think they actually have a good circulation system. So they're not only going to live even longer because they're lower mass, but they're going to live even longer because they can circulate hydrogen into the core so it can be more efficiently fused. In other words, you can fuse a larger fraction of the hydrogen you have. The tranches of stars are basically about 0.08, which is the smallest star possible. Remember, that's about 8% the mass of our sun, which is about 60 Jupiter masses. 8% up to about 0.5 solar masses. That's like extremely low mass star stuff. That's, we're not considering that in this chapter. Then, in this chapter. Then the next section is 0.5 to 3 solar masses, and that's what we call low mass stars, and that's what we're talking about in this chapter. Then from about 3 solar masses to 8, that's medium mass stars. And then from 8 solar masses on up, those are high mass stars. So that's the way we're breaking this down. And we'll talk a little bit about those extremities of 0.08 to 0.5 solar masses, but mainly this is about 0.5 to 3 solar masses. And your book takes a little time to talk specifically about a 1 solar mass star, so you'll have a better sense of what our sun does. Eventually, they run out of hydrogen in the core. The core stops producing energy. That's a problem because remember, the core producing energy is sort of like a balloon that's being pulled underwater, and the water's trying to compress the balloon. Eventually, it's going to get to the point where the balloon's pressure is exactly equal to the pressure of the water around it, and that's what we call hydrostatic equilibrium. Well, that's the same thing our core is doing. Our core is producing radiation energy such that it makes a pressure that's just able to match gravitational pressure squeezing it in. When you stop producing energy at the core, though, then that radiation pressure isn't going up, and instantly the gravity will squish it down really, really small. Well, you could think it might even smush it down to infinitesimally small, which would become like a black hole or like a discontinuity in space, literally a rip in space-time, because you've made something that's infinitely dense or something like that. But we're not there. The pressure is not going to be large enough to do that kind of thing. Because of the low mass, it's going to come to a stop basically when it's forced all the electrons into the lowest level that they could possibly be. And if you know anything about quantum mechanics, even like from a basic chemistry, high school chemistry, conceptual chemistry level, you probably heard of the Pauli exclusion principle, which basically says no two identical particles can have exactly the same quantum numbers. Well, that's what's happening here. When you compress this matter so tight that you're trying to force one electron and another electron into the exact same state, they don't allow that. And we can calculate through some pretty ingenious ways maximum pressure that can withstand. And that pressure really is called the electron degeneracy pressure. There's also another one for the nucleus, by the way. There's a neutron degeneracy pressure, but we're not talking about that either. We're just talking about this electron degeneracy pressure. And it's weird in that it doesn't respond like a gas does, where if you increase the temperature, the pressure goes up. No, this just sits there at a fixed pressure rate based on the amount of mass that's in there, because that dictates the number of electrons that are in there. So you have this electron degenerate state. That's providing the pressure from keeping the core from collapsing further. The gravity will then push part of what was outside of the core is now sort of in the core area. It's going to compress it enough for it to reach that 10 million Kelvin temperature. And that 10 million Kelvin temperature means that now you're going to have hydrogen fusing into helium in a little spherical shell around that degenerate core. And if that actually gets hot enough, or if it forces the other stuff hot enough, we can go to another level of fusion where you fuse helium into carbon, but that takes 100 million Kelvin. So right now we're just talking about The core has now collapsed because it's not producing energy. It's really, really small and compact. And the only thing that's holding gravity at bay is electron degeneracy pressure. And that's not temperature dependent. Outside of that is a shell that's keeping gravity at bay. But now remember, you still have just as much gravity. Maybe you lost a little mass, but probably you didn't lose any. Then all that mass is now being supplied or is now supplying a gravity that used to be taken up by that whole core pushing out radiation. Well, if you're doing that now with a little thin spherical shell, that thin spherical shell is going to have to be a lot thicker to account for the gravity. And that's going to cause the star to expand, because instead of the core being this size, the core is shrunk down this size, and now that thin shell's got to make up for that lost amount of energy, lost amount of radiation to keep gravity at bay, and that pushes the whole star outward. Remember, the Hertzsprung-Russell diagram has these lines of constant radius, so that immediately suggests, because it's swelled up, it should go up and to the right a little bit, just because the increase in size, increase in radius, okay? Any questions on that? So at this point, the star does move off the main sequence. So somewhere, these are the roughly 0.5 to 3 solar mass stars right in here, this little region from here to here. So somewhere along in here, these stars are going to go start pulling off of the main sequence off this way. Star's life depends on the mass and composition. And this is what I was talking about, how we're not 100% capable of predicting everything any star will do, because the composition, small amounts of changes in composition can mean very different outcomes. If you have certain elements present, they might be used for a catalyst for a certain type of nuclear reaction that actually might let the thing live a little longer. But other cases, it might not have that compound, or that, or excuse me, it never has compounds, but it shouldn't have that element. So that could be a problem that makes everything entirely different. So stars of different masses evolve differently. The star's luminosity, size, and temperature change all change during this process. The rates and types of fusion depend on the star's mass. Here's where I was talking about the various categories. In the slides, they're not talking as detailed as they are in the actual reading of the text. So they're calling low mass stars stars less than 3 solar masses, but they're really not discussing less than 0.5 solar masses. The intermediate mass stars are 3 to 8, and then the high mass stars are greater than 8. Stars with the same mass share many characteristics, but again, their end game of life can be quite different, again, because of composition. More mass means that there's more fuel. Luminosity is related to the rate the energy is used. So higher temperature and pressure means faster nuclear fusion, and more massive stars have much higher luminosity. So here's a table showing you how short stars live when they're supermassive. Remember, O be a fine girl, kiss me. That was the spectral type. And O being the hottest of hot, O's being the hot stars, and O0s being the hottest of hot, O9s being the coldest of hot, but still warmer than B0s, and so on and so forth. So you see a O0 or O5 star is likely to be 60 solar masses. It's going to have a 500,000 solar luminosity. So almost it's half of a million times more luminous than our sun, but its lifetime is only going to be about 360,000 years, not even millions of years, 360,000. A B0 star will live to be about 7.8 million. A B5 will live about 1.2 times 10 to the 8. So remember, that's 120 million years for A0, so on and so forth. So you could, in principle, put those values down on a graph and then find keep putting exponents, integers, half integers, quarter integers, all sorts of stuff on the mass and the lifetime until you get a straight line. And when you get a straight line to a curve fit, and that would actually give you the formula. But the formula turns out to be basically the life of the sun divided by the solar mass of the star to the 2.5 power. So this is the formula. Again, not going to be using it. They might ask you a couple questions in homework, but not on our tests. So the energy available, that's proportional to mass. mass to some extent, right? And the rate used is proportional to mass as well. So you're going to see that that's going to come into play. And if you take this equation, divide it by the lifetime equation again, but for our sun, then you'll get everything in terms of solar lifetime, solar mass, and all that good stuff. And you can see that in the working it out. Again, if you like math, check that out. I love this stuff, but it's more than what we're needing. I need you to think life of the star, mass of the stars, thumbs up, thumbs down. Okay. And then you need to know that the power is 2.5, not 2, not 3, not 4. So and I don't even require you to do that much, because it's kind of complicated to say, well, if I double the mass, how does the lifetime change? Well, it changes by 2 to the negative 2.5, and most students don't know what the crap that is. So we're not going to mess with that. So when it leaves the main sequence, it has that degenerate helium core I was telling you about. The star undergoes hydrogen shell burning. So remember, I was telling you there's a little spherical shell around the outside, but now that's got to account for all the energy the core used to make, because it's got to still reach almost the same pressure that the core had to be at to hold gravity at bay, because you haven't lost a significant amount of mass out beyond that inner shell or the core. The gravity crushes helium because the core doesn't provide pressure to oppose it. The core becomes more dense and becomes electron degenerate, as I told you. The weight of the overlying layers of the star. This is the weird degenerate electron C. So these electrons are refusing to get too close to each other, is one way of thinking about it, and that's the Pauli exclusion principle. And that Pauli exclusion principle is preventing them from getting but for so close, and it can put out sort of a maximum amount of pressure, and that's the pressure that it's doing. And the only thing it depends on really is the mass that's in there, because the mass that's in there is roughly related to the number of electrons that you have. So that's a whole nother problem. Hold on a second. My daughter is coming in, and I just realized the door's locked. Be right back.
He locked his daughter out.
I'm sorry, everyone. That was unacceptable. I apologize. I had to leave.
Okay.
So anyways, the electrons become more and more plentiful as more mass falls on the core. And because of it being degenerate, that actually produces more pressure, but only through that mechanism, not through temperature. So what you see immediately is, like I said, the star is going to leave the main sequence, and then it's going to go up and to the right, because remember now that outer shell is got to pump up basically to account for the loss of the core, and that's going to now keep everything at bay. So that'll actually make the whole star a little bit bigger. Plus the reactions are a little crazy. They're doing some stuff through the outer layers, all that good stuff. Eventually it gets to a sort of equilibrium point where hydrostatic equilibrium is reestablished, only this time it's reestablished at a different level. So that becomes this little horizontal branch that you see right here. So that's sort of the equilibrium level. But what happens next is kind of cool. So after leaving the main sequence, the star's luminosity increases. Again, luminosity depends on radius and temperature, right? So the radius actually definitely went up. So since the radius went up, that's going to make, unless the temperature went down by some comparable or a little bit smaller amount, then the luminosity should actually go up. And it actually did go up. As you saw from the radius going up, the luminosity went up. The degenerate core has stronger gravitational pull being compressed on it. The pressure increases on the hydrogen shell fusion layers, and more energy is released. So the inner hydrogen layers are driven outward. And then again, because that expanding spherical shell has a volume of 4 pi r1 squared minus r2 squared, whereas before it had 4 pi r squared. So that little shell volume is now going to make up for that whole spherical volume. So that's pushed it all out. That pushes out the inert hydrogen layers, which means the layers that aren't participating in fusion. Those changes cause the surface area to increase, and that's of course where the radius is increasing, as I told you before with this. It becomes, in fact, a red giant star. It has the degenerate core, the non-fusing degenerate helium core, and then the hydrogen fusing shell, and then the non-fusing hydrogen envelope around it. And at this point, it's actually starting to go on the main sequence branch. So, or excuse me, the red giant branch. It's in the subgiant area, but it's actually following this red giant area, but along a vertical line up and to the right. Okay. The helium core is small, dense, and electron degenerate. The outer envelope is greatly expanded and cooler. Fusion of the hydrogen in the shell creates more helium, making the helium nuclei in the core denser and hotter. So you see the mass on the actual degenerate core is increasing. Specifically, you can think of it this way. Helium is more heavy than hydrogen, and the hydrogen shell is fusing hydrogen into helium. So the helium is going to sink down into the core. So the core gets more massive and more massive. And because of that more massive, it's actually going to get bigger and bigger and bigger. Not because of temperature, which is normally what happens with the core. This is purely because of more mass coming on because it's a degenerate core. The core reaches 120 million Kelvin. So around 100, 120 million Kelvin, that's where we can have what's called the triple alpha process. So first what happens is two alpha particles. Remember, alpha particles is the fancy name. Actually, it's sort of the caveman name, if you will, for the helium nucleus, because they found this as one of the first particles of radiation, and they called it alpha because it was the first letter of the Greek alphabet. And then they found the beta particles, which turned out to be the electrons and positrons. And then they found the gamma particles, which were the photons. So this is the alpha particle was the name it had before they realized, oh, that's the helium nucleus. So now that we know it's the helium nucleus, we'll just still call it the triple alpha process. And you see when two helium nuclei, two alpha particles run together, that makes 4 protons and 4 neutrons, which gives you a total atomic mass number of 8. So that's beryllium. The 4 protons is beryllium. So we have beryllium 8. Now that's going to quickly disintegrate, or it's basically going to decay, because that's not a stable configuration for our nucleus. In fact, it needs a little more number of neutrons to hold that together. So it's rather quickly going to decay into something else. But if another helium runs into it within time, then it will spontaneously go from beryllium 8 to now 4 more particles on it, which makes 12 total nucleons, and it'll be carbon 12, and that will produce a gamma ray as well as the carbon 12. The energy released is carried off by both the motion of the carbon 12 nucleus and the gamma ray. So at this process, you now have some intermittent spots of beryllium being there, but they don't last very long, but you do have carbon. Okay. And you can even go farther. Some stuff will mix with this, but it's a lower probability nuclear reaction. So if you add another 4 to this, it becomes 16. And instead of having 6 protons, it'll have 8, which is oxygen. So you can actually generate oxygen 16 by a 4th alpha hitting this. And that does occur. So you're actually, though you're mainly burning helium into carbon, you're also producing oxygen as well. When this keeps going, this electron degenerate cloud of the core, it keeps piling this stuff on. Once it reaches that 120 million Kelvin, or 100 to 120 million Kelvin, that's actually when this reaction starts to occur, and we get what's called the helium flash. And the helium flash is sort of like a thermonuclear explosion, just like what started the star from a protostar to a star. Only this one's inside the core, so you don't necessarily see this cool flash on the outside. You just see spontaneously, boom, 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 a chain reaction inside of the previously degenerate core. Now the core is kicking in, poof, it expands back out. Of course, the shell around the outside is still burning, as long as it has enough temperature to continue burning hydrogen into helium. And then the inner part is fusing helium into carbon and making some oxygen as well. Because of this, the star can actually shrink, because now the core is going to expand from the heat due to the radiation it's producing. It can now take the lion's share of the necessary gravity fighting, and the shell can shrink back down again. and that's what's going to happen. So the shell shrinks down so much, despite the core going bigger. The overall effect is the star will shrink down a little bit again, and that makes our second our second horizontal branch. So what happened here, and this is again why I don't like it. It went up and to the right a little bit, and then it had a horizontal branch. Then it had this red giant branch, and right here at that peak was the helium flash. It falls back down. That was called the horizontal branch, basically right there. Okay, so it's really quick. So the end point is what they point to and call that the horizontal branch. Now some other stuff's going to happen. After the helium flash, the star is on the horizontal branch. Again, that's the blue line there. Helium fuses to carbon in the core. Hydrogen fuses to helium in the shell around the core. The star is smaller and hotter. Hotter, remember, means going to the left on the Hertzsprung-Russell diagram, so that's why it went off to the left. But it's smaller, so the increase in temperature wasn't enough to overcome the decrease in surface area, which was quite large. I mean, literally like a factor of 1,000 larger. In fact, when our sun does this, or a star like our sun does this, if we replaced our sun with that, and say it had this one solar mass, if we considered a one solar mass star, when it goes through this phase before the helium flash, it would definitely take in the orbit of Mercury and Venus. We're not really sure, because of compounding factors, whether it would engulf the orbit of Mars, or excuse me, of Earth, and maybe even Mars, though. But it could. I mean, that's a very real possibility. It's in the right wheelhouse as far as mass, but a lot of little factors determine that, because each time the star gets bigger, gravity's holding on to those outer pieces even less. And because of that, they can escape. Remember, anytime anything goes about 1/6 the escape velocity for the given body, then over time that thing going 1/6 of the escape velocity will leave. So some of that stuff's going to start to drift out and make what ultimately become a planetary nebula type stuff, or at least a cloud of debris that's propagating outwards. So that's going to be there no matter what. So the horizontal branch will actually stay stable for about 100 million years. That's a long time for us, but remember, 100 million years is only 1/10 of a billion years, and our star is going to live for 10 billion, so that's literally 1% of its life. So the horizontal branch is not that long. It's just a little longer compared to, say, the instant of the helium flash. The core runs out of helium. There are several layers of basically, at this point, when they start to go back up. So you saw, let's go back. You saw that it came down to here. So we had it going here, went to a horizontal branch, and then shot up along the red giant, and then it's going to drop back down the horizontal branch, and then it's going to go up to what we call the asymptotic giant branch. So all of this is where it's going to asymptotically approach whatever type and size of red giant it's going to become. So that's the overall shape that we're talking about here. It's going to do all this stuff. So that's what they're saying. AGB is asymptotic giant branch. The core runs out of the helium. There are several layers of AGB stars, meaning layers of things going in. So for instance, depending on the various masses, you might get to a next critical temperature level that might actually allow you to fuse that carbon to, say, silicon, or that fuses some of that oxygen to something else, so on and so forth. So you could, in principle, get a couple different types of shells, all depending on the conditions that it's allowed, up to 3 solar masses. So in that range from 0.5 to 3 solar masses, you could get some other cores. I mean, not other cores, you'd have a core, but you could get some other fusing shells around the outside. So that's what they're talking about here. The innermost layer, of course, is going to be degenerate carbon. Actually, if the star's not heavy enough, if the star doesn't have enough mass, it won't even reach the carbon point, in which case it'll be a helium degenerate core. So that's a possibility. If it's heavier still than our sun, and then it could actually have something higher than a carbon core. It could have a silicon degenerate core. So that's the key differences, depending on slight variations in masses, but the overall behavior is still the same. Right above the degenerate core will be a helium fusing shell. That's always the case. Basically, the last thing that it was fusing would be the immediate inner shell. So you go from core to the last thing the core was fusing, that would be the shell, and the last thing before that would be the shell outside of that, and the last thing before that would be the shell outside of that. So finally, there is a majority of the star, a non-fusing hydrogen envelope. I don't know what the sentence is saying. Finally, there is a majority of the star, a non-fusing. Oh, okay. So it's saying basically because of this gravity getting weaker and weaker as this thing swells up again with another shell burning process. Okay, eventually so much stuff is going to fall off that the majority of the shell is actually hydrogen shell burning. Okay, so you can lose the first stage that we went through in that horizontal branch, you could lose 10 to 20% of the star's mass. And then while you're on the red giant phase, you're probably not going to lose much. But then on the next horizontal branch, you could lose another 20% possibly. In fact, ultimately, when all this is said and done, a star like ours is probably going to lose maybe 70%, 60% of its mass. So it could be a really, really, really huge mass loss in all of this. So the AGB star, again, this is asymptotic giant branch, expands immensely. Okay, again, we're talking now a degenerate core, which in most cases would probably be a carbon core, right? Because it's been fusing helium into carbon. Then you'll have the hydrogen, or excuse me, the helium burning outside of that, and then you'll have the hydrogen burning outside of that. Now you got two thin spherical shells that have to compensate for what the nucleus or the core was doing. The core is back down to a degeneracy pressure, only this time it's in carbon, but it's still electron degeneracy. And now you have two of those layers, so it's going to expand even more. It's going to get more opportunity to lose more mass. That's why I was saying it might lose another 20 to 30% of the mass along the AGB branch. The large radius means much lower gravity. Radiation pressure is greater than the gravity, so you have stellar mass loss as the outer layers drift away, and it's literally just a drifting because they're reaching that 1/6 of the escape velocity. The mass loss is spurred by the AGB's unstable interior. Again, the equilibrium position is not very good. It basically has gravity pulling down. It's got pressure blowing out, but that pressure blowing out and just drift is causing the gases to leave. So it's becoming less massive, which means the pressure on the inside is actually higher than the gravity on the outside. That's what we mean by it's a rather unstable interior. So it ejected the outer layers, and they make what we call the planetary nebula. So in normal circumstances, you'd expect all this stuff to be equally powerful in any given direction. When you shoot something in all directions equally, then you necessitate a sphere. So that's why you're basically going to get the spherical planetary nebula. But little twerks, like the things rotating weirdly or any stuff like that, can't actually make it do odd things. So you'll get things like this ant nebula and the butterfly nebula and stuff that you'll see in some of the other photos. But what's happening is slowly you're leaving just the core. The core will be a compact white dwarf. It'll be a little cooler than it was on the asymptotic giant branch, but it's still very, very hot. It's basically just the core all by itself, which is hugely carbon with a little bit of hydrogen and maybe even some helium burning shells around the outside that are slowly going to contribute more and more carbon to the core and more hydrogen to the inner shell, and so on and so forth over time. So it'll be super, super hot. And as it cools down, because it's radiating its energy away, it's not making new energy. It's just hot because it used to be inside the furnace of a star. So it's slowly going to cool down, cool down, cool down. It's going to go off on that basically that Hertzsprung-Russell diagram off and to the left and up, and then it'll start to go back down as it starts to cool, and then it'll shoot back down below the main sequence and come in where it's roughly going to stay essentially the same radius. So it's literally going to ride a constant radius line down and to the right on the Hertzsprung-Russell diagram into the white dwarf area. So here's some of those planetary nebula. This Helix Nebula has a lot of spherical symmetry, but you can see there's still some parts that aren't spherically symmetric. And that could just be statistical anomalies, like the fact that at one instant when something happened, there might have been a outnumber of neutrinos in one area than there were in another area, or there might have been way more electrons in one area than another area. All sorts of weird stuff could cause those dissymmetries. Here's a butterfly nebula. That one you can see is very much not spherical. In fact, it's almost like something got in the way along the disk. That disk could be a dust disk, where this might have been a planetary type solar system, a solar system like ours is going to have planets around it. That disk could have stopped a lot of that stuff and made two bulbs instead. Same thing here with the Ant Nebula. And the Cat Nebula looks like something was sort of like a spirograph, like right? So those are my action faces, by the way. But yeah, that's kind of what's going on with those. The conditions are right. The star will ionize the gas in the planetary nebula. So it's going to become like those H1 and H2 regions that we talked about before in the protoplanet stage. So the same stuff is happening here. They get irradiated, but they're also moving away at 20 to 30 kilometers per second. So they're radiating all this light. We can track back, for instance, one nebula in I think it's the Crab Nebula. Basically, we know when that occurred. We know exactly the date that occurred. We look there now and we see a planetary nebula, and lo and behold, you can take the Doppler shift of the planetary nebula and compute what its velocity is, and then you can look the distance between the edge of the planetary nebula and the center where the little white dwarf is. And if you divide that distance by that velocity, it gives you, lo and behold, exactly that date that well, I shouldn't say exactly. It gives you within a few days or at least months, based on error bars, of when we know in recorded history that thing exploded. So that's kind of cool. We can do that. And that's how we sort of confirm what we believe. So we make these wonderful models that are supposed to exhibit how stars behave, and then we get outputs from that, and then we go look for stars exhibiting that type of behavior. And when we find they're doing stuff consistent with our hypotheses, we pat ourselves on the back, and then we go back to our models and make more predictions. If we see something contradict it, we either have to toss the model completely or fix it. Okay, and by that way, the theorists and the experimentalists are working hand in hand to feed each other information that the other can use. It will last only about 50,000 years in general, because eventually it's going to get so dim. Remember, it falls off like a 1/r² thing. It's going to get so dim because it's spread out over such a large area that we won't be able to detect it even with our technology. We think that estimates around 50,000 years. So if anything happened more than 50,000 years ago, we're probably not going to see the planetary nebula. That also gives us a hypothesis that can be tested. If we ever find a planetary nebula, for instance, that's 400,000 years old, then we have to say, okay, we don't understand what the crap a planetary nebula is, or at least this one's a weirdo, right? Any questions on that? There's the whole lifespan. This is the one that I wanted you to keep referring to, because I think it makes more sense when you have the whole picture by to look at while you're going. So what happened here was the star left the main sequence. It did so while there was a degenerate core. Eventually, it reached an equilibrium point that it was sort of happy with. So it did basically this. And as it went on, basically what was happening was we were creating more and more fusion in the actual shell that made it expand more and more and more and more and more. So we went up this giant branch, which is actually just called the red giant branch, but it's in the subgiant area. Part of it is. And then we got here's the helium flash. This is when the helium in the nucleus, or excuse me, in the core of the star exploded and created a thermonuclear explosion inside that we wouldn't necessarily see. But because of that, now the core is in the game, so everything can shrink down along the horizontal branch, and then it reaches a new equilibrium. It'll continue to fuse helium into carbon and some oxygen, just as it's going on its merry way. And then all of a sudden, the core will become a degenerate again, because it'll run out of carbon fuel, or whatever the fuel is, depending on the mass. When that happens, it basically sort of just drifts off and slowly loses its outer parts and comes back here, maintaining a constant radius as it cools down, cools down, cools down. So in some sense, there might be a place where you can go in outer space where we find a white dwarf, maybe hopefully a very, very old white dwarf, so it's not that hot anymore, but it would literally be comparable to 2 or 3 times the mass of the Earth, and it's one giant diamond, because it's literally a 99% carbon ball that's under the greatest pressures we could possibly imagine, probably even higher pressure than we deal with when making diamonds. Diamonds are just balls of carbon that have been compressed to such a high density that they become this diamond sort of, I'd say, I don't want to say state of matter because it's not really that, but it's a form of a compound. And in this case, it's clear, it's transparent, and has beautiful depth. And that's how diamonds are made. Well, guess what? If we could go somewhere in outer space where a very old white dwarf is, we could literally find 2 Earths worth of diamonds, and then all your people that have diamond rings and diamond other things would not be worth very much because we'd have a glut of it in our market. Any questions as we go on? I know I'm sort of on a riff here, but I want to make sure I foster questions. Nada? Okay. Well, the leftover electron degenerate carbon core on the star remains as a white dwarf. It is hot. It cools off in millions of years because it's not producing any more energy. It's literally just hot and cooling. Okay. It's small. It has a low luminosity. Its mass is 0.6 to 1.4 solar masses. In fact, I was saying a couple of Earth masses. This kind of scenario, if it's this large, could be, you know, on the order of tens of thousands of Earth masses. The radius is roughly the size of the Earth. That's where I was getting confused. I forgot and was talking about radius when I said a couple Earths, but it's actually more a couple Earths size in radius, not in mass. Its density is a ton per teaspoonful. So imagine a single teaspoon or a single sugar cube, which is about 1 centimeter by 1 centimeter by 1 centimeter. That thing weighing a ton. Okay. So that thing weighing as much as a truck, say. All low mass stars become white dwarfs. Now, there are different types of white dwarfs, though, as I said, because the core could be made of just helium, and you know, because it never got to the 120 million Kelvin, or it could have gotten even further than 120 million Kelvin and became silicon or oxygen or something like that. So there's different types, but the carbon one would be pretty cool because we get diamonds. So here's the actual picture of what's going on. You can see the main sequence star, say the sun, is fusing hydrogen in its core. It starts fusing hydrogen in the shell around it, and it has a degenerate helium core. It's now a red giant branch star. So you see that's where it's going up right here. It has a runaway helium fusing in the degenerate core. That's right after the, say, helium flash, which occurs right around in here. The hydrogen flash would have occurred over here, by the way. And then it goes to, and I hate the way they've got these arrows crossed. Right up here, we're on the asymptotic giant branch, which has hydrogen fusing in the shell. It has helium fusing in a shell inside of that, and then it has a degenerate carbon core. And then a planetary nebula ejection. So basically it's ejecting the material outside of it, making a planetary nebula. All that goes on while it's commuting to become a white dwarf. Okay. Your bookie, I mean, your smart work will even have sequences like this where you label the individual spots with their appropriate actions going on. Those are really good questions to help you understand this process. Surprisingly, many planets have actually been found in orbit around evolved stars. We know that when our star starts to expand on that red giant branch or even that asymptotic giant branch, that it's going to get so big that it will definitely engulf the orbit of Mercury and Venus, but it might even do Earth and Mars. But there's actually a way that that might not even happen, say, for Earth, even if it got big enough. And the reason being is, hey, each time it sloughs off mass, the mass of the sun gets smaller, the gravitational attraction between the sun or any star for that matter, and the planet gets smaller. This planet's not going to slow down, right? It's just got no reason to slow down unless it hits some of that gas and dust. But even then, it's not going to be a huge thing to cause it to slow down much. So it's still going to have a necessity for a certain centripetal force to keep it in that circular rear or nearly circular orbit. So it's going to keep on doing this, but at that speed, gravity is not strong enough to hold it. So it'll drift out, if you will, and actually become a larger orbital. And in that case, you might actually see Earth as a structure, not as something that supports life, because a long time before this, all our oceans would have evaporated, but you might actually see Earth survive. If not, the dust cloud is going to become part of it and actually could, in principle, fall onto the surface of the white dwarf. And when we look at the spectra of the white dwarf, we would get some really conflicting information because we'd see basically hydrogen, helium, carbon, but it had all this other crap on it. You're like, how the heck did that get there? Well, that's some of the debris from the planets that were sort of sucked in, if you will. Now, that is a typical thing. The planet's actually migrating outward due to a loss of mass of the star. But we've also seen that when you take into account tidal forces of other planets as well as the star, you can actually get planets migrating inwards as well. Your book does a explanation of that in one of the working it out problems. Again, that's mathematics that I don't require my students, but it's certainly interesting. So what happens when you actually have a binary system? What happens when you have two stars orbiting one another? And when they do that, they're really orbiting the center of mass. So again, imagine like a plexiglass cylinder, and you put a supermassive ball on one end and a light ball on the other end. You slowly move your finger under the plexiglass rod until you find out where you could balance that. And obviously, if this one's supermassive, it's going to be really close to that one, right? So that would be the center of mass of the two-star system. This little guy is just going to go in that small of a orbit, while this one's going to go in this big of an orbit. And it's always going to be on, they're always going to be on opposite sides of that center of mass. That's the way the orbits go. Now, what we've learned is that low mass stars live for long, long periods of time. And that high mass stars live for short periods of time, like a O5 star is only going to live about 360,000 years. So what happens when we look up at a binary system and we find that a main sequence star is actually, say, 8 solar masses, and it's orbiting a red giant that is 2 solar masses. You're like, what the heck? How's that possible? Because we know as a binary system, they were born at the same time. But we have a 8 solar mass star that's in its main sequence, which is, the majority of its lifetime, but that's only supposed to last on the order of, say, 100 million years. And then we got this 3 solar mass star that's supposed to last on the order of 1 billion years. It's in its death throes because it's a red giant. Well, that was some of the stuff that immediately made us think this way. It turns out that when 2 stars are close enough, there's things called Roche lobes. Remember the Roche limit I talked to you about before. If something comes within the Roche limit of a planet or star, there's enough gravitational force pulling toward the North Pole and towards the South Pole that it overcomes the ability of gravity to cause that object to accrete into a single object. Because of that, it rips things apart. So anything within the Roche limit gets sucked apart and into the individual planet. Well, if you have 2 stars with their Roche limits right around in here, then if any of the matter of one of these things gets to that point, it's going to be sucked over to the other star. So what could have happened and what did happen was the 8 solar mass guy, which was obviously a main sequence star, but it was 8 solar masses, so its life came to an end quicker than the 3 solar mass one. So it came to an end. It started to go through its red giant phase, so on and so forth. And we're not really talking about high mass stars yet, so I should be a little careful. But let's just say the high end of the 3 solar masses versus the low end of the 0.5 solar masses. So maybe this guy's the 0.8 solar masses, and this one would be around 3 solar masses. This gets to that red giant phase, and then it even gets to the asymptotic giant branch, and it's so large that now it's filled in this Roche lobe. It starts to feed onto this star. Well, that sucks enough matter off where this thing regains equilibrium and it's starting to behave like a main sequence star, whereas this thing has now been pushed over its limit, has like a helium flash, and then starts going into its death knell like a high mass star would. So that's really what's going on. It's a mass transfer going from one star to the other. And when this star turns around, does the same thing, this star can suck mass off of it, and it'll happen all over again. In that sense, you can get sort of a perpetual motion that continues on and on and on between 2 stars transferring mass back and forth. Isn't that kind of a cool story? Well, we've actually seen this too. So we have not only hypotheses, we're actually at the theory point in this point. We've got so much information that we're pretty confident it's right. It does happen. Very confident, I should say, we're right and it does happen. So the end result is you can see weird things like what's supposed to live for a really long, long time, not living for very long, and other things living for very long that are supposed to live very, very long, seeming to not live very long at all. I'm sorry, I've got the mail person delivering stuff, and we've been having packages stolen from our mail, but it happened to several people. So I'm curious if it was the mail person doing it or if it was someone else. And they just sort of cut the side of our package. Doesn't look like they did it this time. Dude's got green hair though. That's crazy. All right, here we are. So the first star to evolve becomes a white dwarf. When the second star is a giant, it can dump material into the white dwarf. That's the whole process. That's the tricky thing about stars changing, or stars in binary system, is they can transfer mass on each other.
You need to go out and get your mail. Go get it.
No, it's just he's taking so long. I've never seen somebody take so long in a mailbox. How's he making any money? Oh, now he's checking his Twitter account.
Hourly.
Yeah.
How's he making money? He's paid hourly.
Yeah, the
Not
worst
by
part is,
package.
the package that got stolen was like a shirt from my Chihuahua. So this dude's like mega rich with a Chihuahua shirt. Anyways, because of this, you can actually get to a point where there's a very specific explosion. It's called a nova, and that just means new. So like what would happen, and this happened several times in history, we have instances where basically during the day you look up and all of a sudden you see a star that's as big as the moon, only it's daylight, right? And it's not really a star. It's sort of this big burst of stuff up in the sky, and it'll stay visible for weeks, 2 or 3 weeks. That's a nova. And it's a very specific type of a nova because it only happens when a certain amount of mass reaches basically that point. Remember, I talked about the degenerate core having a maximum pressure. Once it reaches some critical amount like that, then there's this explosion. That's called a nova. And when you know that, when you see a nova, you know exactly how bright it is because you know exactly what the mass of the star was when it happened. So we can use these as like a standard candle. You can actually look up into space and say, okay, well, I know what the brightness is here. And because it is a nova, it has this very distinct curve we can recognize as brightness as a function of time. We can use that curve to determine, we know exactly what mass it is and use that curve to understand what the luminosity is. Now we have a relationship between luminosity, we have a luminosity and a brightness. So we can use that relationship between luminosity and brightness to tell how far away that thing is. Because remember, luminosity, brightness is just luminosity divided by 4 pi times the distance squared. So we can use these as what we call a standard candle. But it's a very, cool process. I actually was lucky enough to see one. I think it was in M101, which is a spiral galaxy in Ursa Major, if I'm not mistaken. I know it was in that general area. I just couldn't remember if it was in Ursa Major or right beside. I think it was in Ursa Major, but it had a stargo nova. Actually, in that case, I think it was a supernova, not a regular nova. But I did get to see it, and it was available or visible for a couple weeks, and we got to see it with a telescope. Even though in our observatory, the north sky is pretty crappy, but with our nice telescope and the fact that this supernova is so dang bright, in a supernova, which isn't a nova, in a supernova, it's so bright that it's literally brighter than the sum of all the stars in the galaxy. So I literally saw this really bright light that was brighter than the galaxy around it, which you can see is just a smudge. Nova's almost as bright, but not quite, obviously. It's more like basically a 1.6 solar mass star exploding. So that, I said 1.6, I meant 1.4. That limit that I was talking about is called the Chandrasekhar limit, by a guy by the name of Chandrasekhar, who is a person from India. He's a brilliant theoretical physicist. He's passed away now, but he was a brilliant theoretical physicist. He wrote a whole book on black hole thermodynamics. He is really the Mac Daddy. And I do recall him winning a Nobel Prize, if I'm not mistaken. But anyways, what he did was he found that the mass above which the degenerate electron pressure cannot balance gravity is 1.4 solar masses. So that's what the nova is about. Basically, the star keeps dumping mass onto the other star, and that other star has that degenerate core. And when that degenerate core reaches 1.4 solar masses, just like it did before, but inside the star, but now it's not inside the star, it's something that's just the core left, sort of the white dwarf. It keeps throwing mass onto that until that thing reaches that critical temperature. Then you have a really big flash. You have that helium flash that we had before, but now it's like helium flash like we had before, only this time it's a helium flash on the surface, so we get to see the cool nova stuff. The white dwarf in a binary system can get extra material dumped on it, which pushes it over the limit. The white dwarf collapses and explodes in a runaway carbon fusion. The entire star is consumed within a second. So imagine a whole star being consumed to make light and energy. That's what a nova is. It's called a type 1a supernova. The process explained was a type 1a supernova. The explosion releases 10 times more energy than the sun does of its entire main sequence. So this is bright. Like I said, you take and take out all the energy the sun puts out over a 10 billion year span. That's how much energy this thing puts out, and it does so rather quickly. I thought it told us a time period over which it occurs. I guess not, but it's rather quick. Okay, so I'm talking, for instance, not months or anything like that. It's really rather quick. It's weeks. So the other star is left to evolve. Of course, the nova can blow off parts of it as well, and might even make it a little less massive, so maybe it can't go through the following process. But still, this type 1a supernova is a wonderful way of capturing a luminosity and brightness at the same time, so you can use it to determine distance. Here it is. You see it's about 60 light years, 55 light years, negative 25 light years. I don't know why they're putting the negatives on there, but anyways, you can check out those photos. That's the entirety of chapter 16. I think that's, again, you got the process of science and all that cool stuff to read. I think that's a pretty good introduction to what's going on. You'll see, you probably can already guess what other things could possibly happen. Hopefully, I mean, I think you're more imaginative enough to figure out from there where some of those events that have transpired don't transpire the same way. For instance, does electron degeneracy pressure always kick in, or is there some way where when that core stops burning hydrogen and helium, does that core collapse enough to reach that 120 million Kelvin before it gets to a degeneracy pressure? What would happen then? So I think about that stuff a little bit and see if you can predict anything. I think according to our syllabus, we're planned to do the whole chapter 16 for the whole week. So next time I'll have some hands-on type exercises that we can do in real time with one another as the assignment. If I'm correct about that, I'll double check. If I'm right, I won't send you any email to bug you. If I'm wrong, I'll let you know. So does anyone have any questions on this? Nope, nothing, nada, zilch. All right, well, we have lab today at 1. So you can meet me then, and you can, actually, I think I'm leaning towards doing this lab. It's another observational one where you can go outside and find some stars. It looks like we're gonna have a couple days of clearness. In fact, I think today's gonna be clear by tonight. I want you to find the winter circle. The winter circle has a nice mnemonic I use. The mnemonic is 7 ridiculous astronomers caught colds peering at planets. 7 ridiculous astronomers caught colds peering at planets. And it's 7 for Sirius and Canis Major, ridiculous for Rigel and Orion, astronomers for Aldebaran and Taurus, caught for Capella and Auriga, colds peering for Castor and Pollux in Gemini, and then at means nothing but planets is for Procyon, which means before the dog, and that's in Canis Minor. So when you find this, really looks more like a football. It's these, some people call it the winter polygon, the winter circle. To me, it looks like the winter circle, the winter football. It's got these bright stars that even in downtown Virginia Beach and downtown Norfolk, you can see these bright stars, Sirius, Rigel. I want to do this backwards for you, but I'm not, because I'll screw it up, I'm sure. But I see it down here in the bottom. You'll see Sirius. That's the brightest star in the night sky. And then up and to the right, you'll see Rigel, the front foot star of Orion. And then up from that, and again, it changes different times of the night. It's not always up, but from that, you'll see a reddish yellowish star that's in the peak of the V, which makes Taurus's head. That's Aldebaran. And then you'll see a bright bluish star that's Capella, and it's sort of in the Pentagon, but the Pentagon's like got all jacked up when one side's really, really long and all the other ones are normal. And then Castor and Pollux are these two little twins that make sort of a runway that runs into the back of Orion's head. That runway is Gemini, and that top star is Castor, and that bottom star is Pollux. They're the two bright stars, Alpha, Beta, and Gemini. And then you come down beside it and you'll see another bright star, almost about as bright as Castor or Pollux, and that's Procyon. And the story behind that is, as I've probably told you before, the ancient Egyptians discovered that around the time of year that the Nile flooded, in fact, on the very day that the Nile flooded, this particular star, Sirius, which is the dog star, where we get the dog days of summers and stuff like that, they literally thought that star was so bright that it was the reason that the sun was that the summer was warmer than the winter, because they knew from observations that during the day, not only would the sun be up, which is the definition of daytime, but Sirius would be up. So they thought that was the cause of the summer. At least some cultures did. So that's also where we get the phrase "dog days of summer," because Sirius is the dog star in the constellation Canis Major, which means big dog. But they discovered this thing would have what we call a heliacal rising. That means it rises just before sunrise, and then boom, the sun comes out and it's gone. That happens a single day of the year, and that day happened to be very close to or on the day that the Nile flooded. And they're like, wow, this could really help us, because we now understand, if we plant our crops, the fertile crescent is fertile because of the Nile, and the flooding is what makes it so fertile. But if you plant crops in that area and then the flood comes, if you're not on the right time scale, you might actually lose your crops. So they said, well, it'd be really great if we had this other thing that we could use that would warn us a couple weeks in advance, because we don't necessarily know until we made a calendar when the Nile is going to flood or when that star is going to pop up. Well, they discovered by watching that there was another star that came up about 2 weeks earlier, and that star they named it Procyon, which means before the dog. And that's where we got the name Procyon from. So you could use that one.
What?
Yeah, isn't that cool? So Procyon means before the dog, and they got a 2 week.
Oh, I was muted this whole time.
So yeah, that's pretty cool, right?
Whoops. I was like, no one. I even said I was talking somewhat shit to you, Cerise, being like, you should. Oh, I am so sorry.
It's cool.
I was taught. My bad, class. That is my fault.
All right, I was excited thinking somebody got so super excited about astronomy. I'm just cool with that. But no, y'all good.
Yeah, it was half astronomy and half talking with my dad. So I am so sorry about that.
No worries, man. Just don't let me catch you day drinking like I caught some of my other students.
Oh no, no, I'm sorry. That never usually happens.
No problem. Well, we're basically done, guys. I will see you at 1 for lab. If anybody has any questions. Oh, Rosie, did you leave yet? Yep, she did. Crap, boo, crap. Okay, I gotta go check my inbox for that. I'll see her at lab, but I'll see you guys at 1 o'clock. I'm gonna go get me something to eat. But like I said, if any of you got any questions, you can wait around. I'll wait for the last person to leave. And let me know when you do ask questions. If it's something private, I want to make sure I kill the recording before that. I normally do it instinctively, but sometimes I leave it in case there's something learning coming on.
Do we have a test this week?
Yes, and I just told everybody I posted it. It's due on Sunday.
It's on Sunday. Okay. All right.
Yep. The practice test has been up for a week already, but this test will be due on Sunday. 3 attempts.
Oh. Okay. All right. Thank you, sir.
No problem. Have a good one.
You too.
Quick question.
Yeah, Autumn.
A parsec is a measurement of distance?
The what now? The what's a
A
measure?
parsec is a measure of distance.
Yes, it is a measure of distance.
But not... Okay, so... for some reason, I kept getting that wrong.
Yeah, it's
It gives me the question. A parsec is a measurement of time, size, distance, both B and C. And I keep putting distance.
Oh, that's a smart work question, then, right?
Yeah, that is your freaking quiz.
Quiz homework? Okay, I'll check that out. I gotta fix that. That's bad.
I'm like, wait no, it's distance. I know it's distance.
Yeah. I wonder if I was trying to lay it out a little bit and say that it's the size of an object. That's not, I mean, that's an unfortunate way if I did something stupid like that. I'll check it out and clean it up. Thanks for letting me know. Was that chapter 14 or chapter 13?
Yeah, that's chapter 14. That's one of the practice questions. And I'm like, you know, I do these things 100 times. And I'm just like, why do I keep missing this? It's distance.
Hey, oh, by the way, Rodney Clayton emailed me and told me he thought it was History of the Earth, but it seems like they had a bunch of spin-off shows, one for History Channel, one for BBC, that were actually series with the same title. I think the deal is the actual movie that he was referring to, which I found exactly once in YouTube, is History of the Earth, and it was made in 2007.
Okay,
so
cool.
I want to try to find that, and if you could help me find that, that'd be great too, because I'd really like my students to be able to watch that.
The History of the
at
Earth?
least in the 131 class.
Yeah, no, that is a great filmed show for that start class. The history.
Yeah,
of the Earth.
how the continents move over time, and how there used to be an ocean right here in North Carolina, in Western North Carolina. Even.
Yeah. There used to be History of the Earth, the whole history of the Earth and life.
Yeah, it's kind of cool stuff. I love that just that long term of history. I like imagining the Earth without humans and how friggin' huge it would be. I mean, what would it feel like to have all that space to you, and I guess it's a little short sighted because it's you and all your fellow buddies or whatnot, which are the same species.